What's up, me wagons? Welcome back. Today, we're going to start Unit 6. This is going to be so exciting because you folks get to learn a new math operation today. Unit 6 is all about exponentials and logarithms, and you're probably thinking to yourself, oh no. Oh, goodness gracious. You know, my three greatest fears are already, being honest with myself, swimming, and new math operations. Well, sorry, kid, you got to deal with it. You got to grow up someday. You know, someday you're going to have to be honest with yourself, learn to swim, and do new math operations. You're going to have to do new stuff every day of your whole adult life, so get used to it, nerd. So, what we're going to talk about today is the new math operation, which is a logarithm. So, don't worry, I'll tell you what it is and how it works and what it does. So, let's go. Let's go learn some logarithms. So before we learn what a logarithm is, let me set the stage. Let me serve you an appetizer to prepare you for this gourmet entree of a new math operation. Let's talk about inverses. An inverse in math is just anything that used to undo something else. It's the opposite. It undoes it, it gets rid of it, it cancels it, however you want to think, right? The inverse of adding is subtraction, and this is actually bi-directional. It goes both ways. Subtracting is the inverse of adding. All right. Multiplying is the inverse of dividing, and dividing is the opposite of multiplying. Squaring is the opposite of square rooting, and really we can generalize this to exponents are the inverses of roots in general, right? X to the third power, the inverse of that is a third root. So we want to know, and when we say we, I mean me. And when I say want to know, when I'm talking about you, I mean you're forced to know, right? That's how this works. If I have, instead of x to the fifth power equals 25, I want to know, if I have 5 to the x power is 25, how do I figure out what x is? Because you can't just do an x root, right? Because then the root cancels, and you get 5 equals, what is the x root of 25, though? Like, what? Like, well, that doesn't make any sense. How do you take an unknown level of rooting of something? You can't. So we need a new math operation to solve this problem right here. And that math operation is a logarithm. So a logarithm is the inverse of raising a number to a variable. Okay. So in order to get the variable by itself, what we need to do is an inverse operation to remove the base from it, so to speak. And that inverse is a logarithm. I will abbreviate it as log a lot. I'm going to say the log of, right? So, and we're going to practice this, but 5 to the power of x equals 25 can be undone by turning into a log like this. So log base 5 of 25 equals x. And now the x is no longer in the exponent, and we can solve for it as long as we know how to do the log base 5 of 25. And just so we're clear, if I say this out loud, the way you say it is log base 5 of 25 equals x. So this little subscript, which is the opposite of a superscript or an exponent, subscript is the base, right? That's the fancy word for that. It's a base. Right. Okay. So what does log base 5 of 25 equals x mean? What this means is the log expression equals the exponent that makes the equation true. What we're asking, what log base 5 of 25 equals x is asking in words is 5 to what power? You can think of the what power part as x is 25. Okay, so we're saying 5, the base to what power gives me this number? What is the exponent that I put on this number to get that number? And then the answer is whatever the answer to the log equation is. So you're going to say, how does this question undo it? How do I do a logarithm? And the answer to that is not very simple. You really can't do a logarithm, right? There's no like algorithm to do log base 7 of 25, right? You can't say 7 to what power equals 25. I can't show you the process to do this, right? There isn't a process. The way that you get this, the calculator. And you may be curious, how does the calculator get it? And that question is very hard to explain to you. The short answer is the calculator does calculus. It does a process like 10,000 times to kind of get really close to the answer. It guesses and checks like 10,000 times and then gives you the best answer it can think of, basically, is the way it does it. But there's not an algorithm that an Algebra 2 student can follow to do this. So the short answer is you don't do a log. You set up the log equation and put it into a calculator. So let's talk about ones we can do, though, because there are some of them that just by rewriting it as an exponential, we can sort of guess the answer. So let's look at some of these ones that we can guess the answer of. So when we look at log base 3 of 81 equals what? What we're asking is 3 to what power equals 81. Okay, so we can just do 3 to some powers until we get to 81. So 3 to the first power is 3. 3 squared is 3 times 3. So it's this number times 3 again is 9. 3 cubed, 9 times 3 would be 27. And then 3 to the fourth power, 27 times 3 is 81. So the exponent we need here to turn 3 into 81 is 4. So log base 3 of 81 equals 4. Make sense? You're just looking for what exponent turns this number into this number. All right, let's look at this one just to make sure we're clear. So we're looking for 2 to what power gives us 32. So 2 to the first is 2, and then 2 squared is 4. 2 to the third power is 8. We're just multiplying by 2 over and over. So 2, 4, 8, 16, 32. This is 2 to the fifth power. So the answer here is 5. We're looking for that exponent. Pretty easy. Okay. So let's talk about how do we rewrite equations from log form to exponential form. So when we are doing this, if we have it in exponential form, this a is called the base. This x is obviously called the exponent, sometimes called the power. And then b is just the answer. Okay. In this, a is still called the base. Those keep the same name. When b is inside the logarithm, and you're going to say it doesn't look inside the logarithm, it's not like this, Mr. Barton. It's not like that. But when it's next to the log, when it's log base a of b, the of that you say implies that there are parentheses there. So it's inside the log's parentheses. This thing is called the argument. It's the thing you plug into the log. And then now x, which was our exponent, is just the output or the answer. Okay. So what we're going to do is we're going to look at this and then move all the pieces into the correct spots and rewrite it as a logarithm. So if we look at 3 squared equals 9, you're going to write log every single time. That's just the math operation. The base of the log, or the subscript right here, is whatever number has the exponent on it. So we're going to write a little 3. The argument of the log is whatever the answer of the exponential is. It's the thing on the other side of the equation that the base with the exponent equals. So we put the answer inside, equals the exponent. So x. Sorry, not x. 2. Because it's a 2 right there. All right. So write our log. The base is the base. The answer turns into the argument. And then the log tells you the exponent. One more time. Log, the base is the base. The argument is whatever the answer is. And it tells you the exponent. The exponent. Pretty easy. Okay. Let's practice going the other direction. If they're in log form already, how do we rewrite them in exponential form? So our base is the thing that gets the exponent on it. The exponent is what we're looking for. It's what the logarithm tells us. Equals whatever is inside the log. The base is the base. The exponent is what the log is equal to. And the answer is whatever's inside the logarithm. The base is the little number. The exponent is whatever is on the other side of the equation from the log. And it equals the thing inside the logarithm. And that's how we rewrite them. All right. So now let's talk about some just semantics, right? We know in roots, if we have a root and it doesn't tell us the index, it's an invisible 2. The same way, if you have x plus 1, the invisible coefficient here is a 1. So we have a lot of invisible numbers in math that we know just because if we don't write them, we've all agreed that they're a certain number. Logs have that too. So if you have a log without a base, like log of 100, there's an invisible base here that everyone has agreed to use. That invisible base is 10. So if you see log 100 equals 2, the invisible base they're not telling you is a 10. Okay. On your calculator, if you look at your calculator, then somewhere on here, there's a little log button. When you press that, your calculator will say log, and it'll put some little parentheses there. It won't put a base on it. The log button on your calculator is log base 10 when it doesn't tell you the base. A lot of calculators you actually can't type a base into. So you're going to say, that's really annoying. Why not? Because a long time ago, I don't know, calculators didn't exist. You just looked them up in a book. When my parents were in high school, they had this really big book. I forget what it's called, but it's just like a math reference book. And there would be like 100 pages of just log base 2 of 3 equals 1.13 blah blah blah, right? And it'll just tell you the answer to this log problem. And there's like 100 pages of just answers to log problems, and you had to look them up in a book. You couldn't type them into a calculator, because when my parents were in high school, calculators were like too expensive and they were like too niche that not everyone had them, right? It's like not all of you have a really nice computer that can do like 3D rendering because it wasn't necessary, right? Not all of you 3D render. Maybe 30 years from now, that will be the most important thing in high school is learning to render things in 3D. But until everyone needs to do it, we're not all going to have a thing that lets us do it. So, All right. So let's evaluate some logs without a calculator. Okay. This is just what we were doing earlier. We are going to look at the base. We're going to rewrite it as an exponential and then guess the exponent. So if I rewrite this in exponential form, this is 3 to what power equals 27. So 3 times 3 is 9, times 3 again is 27. So we need an exponent of 3. So this will equal 3. Okay. 7 to what power is 49? Well, 7 times 7 is 49, so that'd be to the second power. So it equals 2. All right. We don't have a base here, so the invisible base is 10. So we want to know 10 to what power equals 1,000. So 10 to the first is 10. 10 squared is 10 times 10, which is 100. And then 10 to the third is 100 times 10, so we add another 0, and it's 1,000. So because the exponent is 3, the answer here would be 3. Now this one is tricky. Be very careful about how we rewrite this. We want to know what this is equal to. What's x? Our base is 144. To the power of x equals 12. Okay. So here's where, remember fraction exponents? If our exponent was a fraction, 144 to x over y, we want to rewrite this as a root, right? We have the y root of 144 to the power of x equals 12. I want to take the square root. The square root of 144 is 12. We should know that. So we want y to be a 2, and then I don't want to do it to a power, so x should be 1. So y over x would be 1 over 2. So the power here, to take a square root, we want our exponent to be 1/2. So if your base is bigger than the argument, you're going to get a fraction as a answer. All right. So using a calculator, there's some calculators that do have like a log AB button. And then when you put this in your calculator, it'll say log. It'll put like a little box here for you to type the base and a box here to type the argument. But not all of them have that. So we're going to have to use log base 10. So let me show you the change of base formula. Okay. If your calculator only has the log button, we need this base change equation. So log of some base of some number can be rewritten as log base 10 of the number on the inside divided by log base 10 of what we want the base to be. And then that will help us type into our calculator quickly. So let's look at these. Log, because there's no base here, it's a 10 of 17. This one, we can just type straight into our calculator if it just has the log button. So we would just hit, if I can find mine on my calculator. Oh no, where is it? Do I not have one? Oh no, that's not good. Hold on 1 second. I've got to find this. All right, sorry, I was struggling. I found it. Log base 10 of 17, you just hit in your calculator log 17, and it will spit out the number 1.23045, and that's it. If we want to do log base 12 of 57. And we don't have the log with the fancy base. Here's how we could type it in. It will be log of the argument divided by log of the base. And then that will give us the correct answer. So let me just type that into my calculator. And this tells us it is 1.62704, rounding. All of these are, of course, rounded. This one we could actually do without our calculator, but let's use our calculator just to see what the answer is in case we're having a little block. So to write this with the base change formula, we'll do log of 1 over 16 divided by log of 4. And it's going to tell us that the answer is... sorry, let me type mine in. -2. Yeah, right. This is 4 to the -2 power equals 16. Sorry, equals 1 over 16. If we have a negative exponent, it's 1 over the base to that power, 1 over 16. So it's 4 squared, 16. We could have figured that out. All right. This one, we've got a weird decimal. We just have to use the base change formula. So it's going to be log of 2.55 divided by, divided by. The base here is 10. So we just type log of 2.55 into our calculator. Log of 2.55. And it is about 0.40654. Just type into your calculator. I bet Desmos has a log button. Yeah, but you know, it shouldn't be too hard. If you're having trouble figuring out what calculator to use, ask me. And that's the end of your notes. So go ahead, go try your logs. Hopefully it's a quick, easy lesson for you. Most of it's on the calculator, I think. So until next time, make sure you subscribe. Maybe even tickle that little like button. And I'll see you guys next time. Have a great day.